Okay, moving on. Problem 2 was kind of tricky. It's a 3D problem. This is the lawn sprinkler problem. So we have, from the top view, I'm going to draw a little diagram here. From the top view, you have the sprinkler, and it's spinning around. So say there's the the base of the sprinkler there, and this little metal bar on top is where the water gets pumped out, and this part spins around. So let me actually draw this in a different color. So that part spins around, we'll say, counterclockwise there. And the radius, well, the distance from the center of the sprinkler, or the point it's pivoting about, to one of these holes, oops, that's a little far off. We'll call that R equals 0.2 meters. Okay, so there we go. And this is also 0.2 meters. So from the center out to one of these holes is 0.2 meters. The sprinkler is spinning around, and it spits water out. And the water comes upward out of the holes. So what you can imagine here is, say this is like a side view here, and here's the sprinkler base, there's the lawn, and here's when the arm is like pointing straight at us in the picture, or straight at us looking at the picture. So this is when the arm is lined up along our line of sight, but the arm is moving this way, right, because it's spinning, so it's spinning like that, and it shoots the stuff upward. So relative to the arm, the water goes straight up, but what happens is, because of the spinning motion, you get this initial velocity that way, and the water goes like that, and it hits the ground. And we're supposed to ignore the height of the sprinkler, so the fact that the water starts with some elevation, we just ignore that and say it starts at 0. And how far is it? How far out does the water get from the center of the sprinkler is what we want to know. So we draw this from above. The path the water takes, because the water, what's inside the sprinkler is going this way, right? And then the sprinkler just like shoots it up, so it just like pops out the top of the hole. So the water keeps going this way, but it's going up in the air, like towards us in this top view. So we're looking down from above. The water comes up towards us and then falls back down to the ground over here. So this is a side view down here, and hopefully you can sort of put these together and understand what's going on. So what we know is that the period of the sprinkler is, I believe, 1 second. And so first we want to find out how fast the arms are moving, or these holes are moving, when the water comes out. So this is pretty easy, actually. We'll just take our equation for period from the radius and the velocity, and that's it. And so we just actually flip the, just algebra. You can multiply both sides by v and then divide by t, and you get over to here. Okay, v equals 2 pi r over t, more or less. And then you get, so you get v equals, 2 times 3.14 times 0.2 all over 1.0, and that equals 0.4. 0.2 times 2 divided by 1 is 0.4 times pi, and it equals something like, let's see, 1.256 meters per second, if we want to sort of be super precise, sort of, maybe. Okay, so that's right. So that's what we get for the velocity of the water horizontally as it comes out of the sprinkler. So Vx, and we know, of course, the acceleration is all gravity downward, so there's no acceleration horizontally. So this is just the acceleration due to gravity, straight downward. Okay, so what's our vertical velocity here? Well, what we're told is that initially, as the water comes out, it's going 5.0 meters per second upward. So the time it takes to go from the top to the bottom, or go up and then down, remember that if we've got something moving in a parabolic projectile motion over level ground, it hits the ground with a y velocity that's the negative of the y velocity it started with. So at the impact, Vy here is going to equal negative 5 meters per second. 0.0 actually, but what's a 0.0 between friends, right? So the change in y velocity is the final Vy minus the initial Vy. So it's negative 5 minus 5. So it's negative 10 meters per second. So this is actually pretty easy then. So acceleration equals delta v in the y direction divided by delta t. Let me see if I can scroll down a tiny bit there. There we go. Okay, delta vy over delta t. And that acceleration here is negative g. So I'm going to use negative, and again I'm using 10 for g to make the computation easier, because then you get this negative 10 meters per second squared, or sorry, meters per second over delta t. And so then you get delta t equals 1.0 seconds. Okay, because this negative 10 is negative, obviously. All right, so the water spends 1 second in the air, and you know its initial horizontal velocity, and it stays the same, throughout, is 1.256 meters per second. So this is very easy. Delta x equals vx delta t equals, it's going to be just going to be 1.2. I'll just go ahead and round one here. 1.26 meters. Okay, that's great. Now the trick here is that what I asked, or what the problem asked, was what's the distance from the center of the sprinkler. So we can say right here, this this moves to the impact point. It moves 1.26 meters in this direction. But remember, the sprinkler center is right here, and that's 0.2 meters above. 0.2 meters, it's just this to this. So what we really want to find is distance from the center of the sprinkler, which is this. So this is all just drawing a triangle on the ground from the center of the sprinkler to the point where the hole shot the water out to where the water landed, and it makes a right triangle because this is a right angle. Remember, the velocity initially is always going to be tangent to the circle, which means perpendicular to this radius. So the distance, the water travels, I'm going to call that d. d squared is going to be delta x squared plus the radius of the sprinkler squared. So let's go up here and say d squared equals 1.26 squared plus 0.2. I'm still in view. Okay. And so d squared equals, let me see if I can pull my calculator out and do this real fast. It's not going to be much different from 1.26 because the radius of the sprinkler is pretty small. So d squared equals, I get 1.628. And I guess the units on that would be meters squared, but it doesn't really matter because we're not sticking with that. So square root of that is 1.28 meters. So that's what I get. You'll have something slightly higher if you use 9.8 for g, because that's like 2% less gravity than 10. So the water would stay in the air, probably 2% longer, I guess, and then it would go, a little bit further. So, but that's about the answer you should be getting. Maybe 1.3 something for a slightly lower value of g. So that's problem 2.